Okay, so this is a short video just introducing Chapter 3, Section 6. So the topic is curve sketching. And we did curve sketching in Chapter 2 of Precalculus. And what we did was we looked at the end behavior of polynomials. We looked at the x and y intercepts. So the y-intercept was you set x equal to 0. The x-intercept, you set y equal to 0. This a lot of times involve factoring. Sometimes we use symmetry. We're able to look at the function and know what the domain and range are, depending upon whether the highest order exponent was odd or even, as far as the range is concerned. Polynomials, the domain is all real numbers. We've talked about continuity in this class. Usually where we're discontinuous for most cases is where you have vertical asymptotes. That's where the denominator of a rational function equals 0. If it's differentiable, then we should be able to find relative extrema using either the first derivative or the second derivative test. We can talk about concavity, looking at the sign of the second derivative. And where the concavity changes, we call that a point of inflection. Those points of inflection occur only at points where the second derivative is 0 or is undefined. We talked about horizontal asymptotes in the last section, and we talked about limits at infinity. That's slant asymptotes. So some of these things we did in precalculus, some that we're doing in calculus. Okay. So this is it, what we do. First you determine the domain and range of the function. You determine the intercepts, the x and y intercepts, just like in precalculus. You look for the horizontal and vertical asymptotes. Now sometimes we might do step 3 first, which we'll see in our first example. But we also can use the first derivative and second derivatives and their signs to know if we have local minimums and maximums, whether we have points of inflection. Okay, so that's kind of what we're going to do. We're going to look at some examples. So the first example is this polynomial, and the reason it's all written out here is because I just did it and then my microphone headset wasn't working, so I'm just not going to redo everything. So let me just show things as I go along. So this is a third order polynomial, which we've sort of done already, but we're just going to go through all the steps. What we did was find local minimum and maximum points of inflection. We didn't talk about zeros or intercepts. So, with a third order polynomial, you're either going to have one real zero. This is an example right here in the corner. So you have the function does have concave down and then concave up. So there's a point of inflection, but there's only one x-intercept. Or you could have the ones that we see more often, just because they're more interesting, is where it loops back down and you have a local minimum and a maximum local minimum. So our domain, because it's a polynomial, is all real numbers. You can show that in 3 different ways, or these are 3 different ways you can show it. So you can show it as this inequality, x is greater than negative infinity and less than positive infinity. You can show it as this ordered pair, where the first number is the negative extent of the domain, and this is the positive extent. We use a curved bracket to show that we don't include the endpoints in the domain. Or you could say all real numbers, and infinity is not a real number, so that's why it doesn't count infinity. And the range, because it's a odd-ordered polynomial, it's to the third power, then it's going to be all real numbers. Now, if it was an even power, we don't have all real numbers, depending upon which way it's oriented. It's pointing upwards, so there's going to be some minimum y value that the range will include. In this one, when it's pointed downward, there's going to be a maximum. And that happens. This looks like a parabola, but any even exponent in the highest order term is going to give you something similar to that. So that's the domain or range part. Now the y-intercept is simple because you just set x equal to 0 and these three terms will disappear and all you're left with is your constant. So what we can say is that the function at x equals 0 is equal to 20, or we can say the y-intercept is the point at 0, 20. X equals 0, y equals 20. Okay, now for the x-intercept you set y equal to 0, so that's the function value. And then you got to figure out how to factor this. It's going to have either 1 or 3 real zeros to this expression. And remember what you did is you used the, in pre-calculus, you would use the rational zero test. So what that means is you take the factors of 20, which is the constant term, and the factors of 20 are 1, 2, 4, 5, 10, and 20. And they can be either plus or minus. And then you divide by the factors of the coefficient in front of the highest order term. The factor in front of the highest order term is 1, so you divide by plus or minus 1. So ultimately, what you end up with is 12 possible rational zeros. Now, there's no reason why it should be rational. The only reason is because somebody's made the equation so it works out that way. Most likely it's not going to be a rational zero in real life, but in math, a lot of times they do give you rational zeros. So, you know, what you do is you just try to pick out something that makes sense. Now, because you have the y-intercept of 20, that means, and because it's a leading coefficient here is positive, it's going to have to look either like this one or this one. You know, it's going to start at negative infinity, come up here. Somewhere it's going to go through the x-axis. And with a y-intercept of 20, we'd look at this little graph here. You can see this one goes through y equals something. So I know that I have to have at least a one negative 0. So I probably would start picking negative numbers, which in this case I didn't, but did I? Yeah, I didn't use that in this. I just started picking numbers. So if you use synthetic division, here's the coefficients of the polynomial. Here's the 0 that I'm trying out. So you bring this down. 1 times 1 is 1. 12 plus 1 is 13. 1 times 13 is 13. 13 minus 5 is 8. 1 times 8 is 8. 20 plus 8 is 28. So what you're looking for to find zeros is that this remainder is 0. But it's not completely wasted time because we know that the value of the function at x equals 1 is 28. So we do have a point, 1, 28. How useful that is in helping us, I don't know yet. So then you just pick another one. You know, let's pick 2. So you go through the same thing. Bring that down. 2 times 1 is 2. 12 plus 2 is 14. 2 times 14 is 28. 28 minus 5 is 23. 23 times 2 is 46. 46 plus 20 is 66. So again, it's not 0, so that's not one. X equals 2 is not a 0, or x minus 2 is not a factor. So in the next video, you'll see that I continue on in this thought process. So I'm going to stop. Go ahead and watch the whole next video.